Hello and welcome to this video on building a serverless backend with generative AI integration for contact forms using AWS Lambda. In this video, you'll learn how to create a Lambda function that handles form submissions on your website. So when a visitor submits a form, your Lambda function will process the input, use Amazon Bedrock to generate AI-based content such as a unique greeting or another type of creative message, and then send email notifications via Amazon's simple email service to both you, the website owner, and the form submitter. You may be wondering why you are incorporating Amazon Bedrock into a contact form solution. Well, it's a fun way to add personalization and dynamic content to your automated messages, and it's also a great opportunity to integrate generative AI into a serverless architecture, all without managing any servers yourself. To follow along, you'll need Amazon SES already configured. If you have not set that up, please see my existing content here. In this video, you will cover the following objectives. Explore how Lambda can efficiently power your backend logic without the need to manage servers. Learn how to create a Lambda function that captures form data, integrates AI services, and triggers email notifications. Request access to the Bedrock model and connect it with a Lambda function to generate dynamic text. Set up AWS identity and access management permissions and configure environment variables to store simple email service, sender addresses, Bedrock parameters, and other important settings. And finally, send sample form submissions to test end-to-end functionality and use Amazon CloudWatch to monitor performance or troubleshoot issues. By the end of this video, you will have a fully functional AWS Lambda function that seamlessly processes contact form submissions, generates AI-based content, and sends emails to both you and your visitors, all without provisioning or managing servers. Let's get started. AWS Lambda is a serverless compute service that lets you run code without provisioning or managing any servers. It is like having a virtual computer in the cloud that can process data and perform calculations. When you use Lambda, AWS takes care of all the underlying infrastructure, such as servers, operating systems, and scaling, so you can focus purely on writing and running your code. Within your serverless contact form solution, AWS Lambda will automatically run the code that handles new form submissions. So each time someone fills out the form, Lambda is triggered, processes the data, and handles the rest of the workflow, such as sending emails or integrating with AI services. By using Lambda, you can concentrate on the application logic, while AWS manages behind-the-scenes operations like scaling and server maintenance. Next, you will explore Lambda's key features and how they benefit your serverless contact form solution. Lambda operates on an event-driven model where functions are automatically triggered in response to specific events. An event can be many things: an HTTP request, a file upload to Amazon S3, or even a custom application alert. Whenever an event occurs, Lambda runs your code, processes the event data, and manages the computing resources. After the code finishes, Lambda releases those resources and waits for the next event. In your serverless contact form solution, the event-driven model works in a straightforward way. So when a visitor submits the contact form, JavaScript on your static website captures the data and sends an HTTP post request to Amazon API Gateway. This request triggers AWS Lambda. The Lambda function receives the form submission data and executes three main tasks: sending a notification email to you about the new submission, generating AI-based content with Amazon Bedrock's language model, and sending a confirmation email to the visitor that includes the AI-generated text. Once these tasks are complete, the function finishes executing and AWS reclaims any resources in use. Lambda then returns to a waiting state, ready for the next contact form submission or other configured event. This cycle repeats for each submission, meaning the function runs only when needed, creating an efficient, scalable solution without the need to run dedicated servers. One of Lambda's most powerful features is its ability to automatically scale. Lambda can increase or decrease the computing resources allocated to your function based on how many requests are incoming, without requiring any manual intervention. Automatic scaling offers several benefits for your serverless contact form. First, if multiple visitors submit the form simultaneously, Lambda spins up additional instances of your function to process each submission independently, avoiding bottlenecks or queues. Second, Lambda adapts automatically to varying workloads wherever the form receives one submission per day or hundreds in a short period. You will not have to provision extra servers or worry about running out of capacity. And finally, if generating AI content or sending emails takes a few seconds, Lambda can still begin processing new submissions while other instances finish their task. This parallel processing ensures that no submissions is forced to wait unnecessarily. Now, Lambda uses a pay-per-use pricing model, which goes hand in hand with its scaling capabilities. This model is particularly helpful for serverless applications or any use case with unpredictable usage patterns. Here's how it works. You're only charged for actual compute time. If the function isn't running, you aren't paying, and costs are based on the number of requests and execution time measured in milliseconds. To illustrate why this is cost-effective, compare it to a traditional server setup. Traditional servers incur costs around the clock, wherever or not they are actively handling requests. In contrast, Lambda only bills you for the time your code is actively running. So by adopting a pay-per-use model, you remove the need for capacity planning or detailed server management, streamlining your architecture and lowering costs. Lambda also integrates seamlessly with a range of AWS services, enabling you to build complex systems from simple components without unnecessary complexity. So in your serverless contact form solution, Lambda works particularly well with Amazon API Gateway to handle HTTP requests from the contact form, Amazon Simple Email Service to manage email sending for confirmation and notifications, and Amazon Bedrock to generate AI-based content, adding a personalized touch to your automated emails. Lambda can also simplify the development process, as it eliminates the need to manage servers, allowing you to focus on writing code. In your serverless contact form solution, this means concentrating on processing submissions and leveraging integrated AWS services without getting bogged down in infrastructure details. So without Lambda, the development process would be more complex. You would need to provision and configure a server, such as an EC2 instance, to host your application, which involves selecting the right instance type, setting up the operating system, and configuring security groups. You would also need to install and configure a web server, such as Apache or Nginx, to handle incoming HTTP requests. Setting up and maintaining the runtime environment, like installing Python, would fall on you as well. In addition, handling varying loads typically requires implementing auto-scaling groups and load balancers, which increases the complexity of your infrastructure. And finally, you'd also be responsible for monitoring server health, applying security patches, and performing ongoing maintenance tasks. With Lambda, you avoid all these infrastructure challenges and focus solely on core functionality, making development simpler, faster, and more cost-effective for your contact form solution. While Lambda offers many advantages, It is important to be aware of certain considerations, especially for your contact form solution. First, Lambda functions can experience cold starts when they have not been used for a while, resulting in slightly longer startup times for the first invocation. This is typically not noticeable to users submitting forms intermittently, but it can be more significant for applications requiring split-second responses. Second, Lambda functions are stateless, meaning they do not retain information from previous invocations. So each time a Lambda function runs, it starts fresh, which works well for independent form submissions. However, if you need to track information across submissions, you'll need additional AWS services such as Amazon DynamoDB or Amazon SQS. Third, Lambda has certain resource limits, including up to 10 gigabytes of memory and a maximum execution time of 15 minutes. These limits are more than sufficient for your contact form solution, and you are unlikely to approach them under normal usage. Now that you have covered the key considerations for Lambda, you can move on to creating the serverless contact form solution in the AWS Management Console. Before we dive into the demo, I've got something to help you get started. I'm adding 5 AWS credits, each worth $20, to support anyone who wants to deploy this solution themselves. To redeem these credits, go to aws.amazon.com/AWS credits and enter one of these unique one-time use credit codes. Please note, only one code can be redeemed per AWS account. To begin, access the AWS Management Console and go to the Lambda service. Click Create Function and keep the default author from scratch for a custom function. Name the function Contact Form function. Choose the latest Python runtime version, and for architecture, keep the default setting. On the permissions, click Change Default Execution Role. An execution role is an IAM role that grants the Lambda function permission to access AWS services and resources. For now, keep the default option, which allows the function to upload logs to CloudWatch for real-time monitoring and troubleshooting. We'll add the specific permissions for Amazon Bedrock and Simple Email Service later to allow our function to use these services. With the Lambda function created, let's configure its basic settings. Click on the Configuration tab and under General Configuration, adjust 2 parameters. Keep the default allocation of 128 megabytes for memory, which is enough for processing form submissions and making API calls. Set the timeout to 10 seconds to provide enough time for the function to process submissions, generate quotes, and send emails. These settings are chosen based on typical requirements. After deploying the function, you can use CloudWatch logs to monitor its performance. The logs will show the maximum memory used and the duration of each invocation. If the function is using close to 120 megabytes or frequently timing out, you can increase these values. For now, these settings provide a good starting point for our Lambda function. You can always adjust them later based on real-world performance data. Now save the changes to apply them to your function. Next, let's check to make sure the Lambda function has the necessary permissions to interact with other AWS services. In the left sidebar, click the Permissions option to view and modify the function's permissions. Here, you will see information about the execution role that was automatically created when the function was set up, which currently has CloudWatch logs permissions that allow the function to create a log group, create log streams, and write log events. However, specific permissions for Amazon Simple Email Service and Bedrock must be added. Click on the role name to open the IAM console in a new tab. Now in the IAM console, permissions can be added in 2 ways. Inline policies, which are directly attached to this role, or managed policies, which are reusable and provide better visibility across multiple roles or services. For this demo, we'll use managed policies because they align with AWS best practices. Now, start by creating a policy for Amazon Simple Email Service. Click Policies in the left-hand menu and click Create Policy. In the Service field, search for and select SES. Under Actions Allowed, select Write and check Send Email, which grants permissions to send an email message. Under Resources, keep the default setting to specify resources explicitly. In Identity, click Add ARNs and enter the verified email address or domains the function can send from to ensure secure and restricted access. Ensure that Amazon Simple Email Service is configured with verified email addresses or domains. If you haven't done this yet, watch the video linked here for guidance. For Resource In, keep the default selection of this account, ensuring the function only works within your AWS account. For Resource Region, enter the region where your SES service is set up. This links the function to the correct SES region. For Resource Identity Name, enter the verified domain name that will be used for sending emails. Click Add ARNs to add the specified domain to this policy. Click Next. Give the policy a name, such as SES Send Email Policy, and click Create Policy. In the Policies section of the IAM console, click Create Policy to start creating another policy, but this time for Amazon Bedrock. Under Actions Allowed, select Read and check Invoke Model. This permission allows the Lambda function to use Bedrock's model to generate text. Under Resources, choose All Resources. While this is less restrictive, it provides flexibility to experiment with different models without frequently updating the policy. Click Next. Name the policy Bedrock Invoke Model Policy and create it. Now return to the Lambda console and click on the execution role again. Click Add Permissions and attach policies. Search for and select the policies you just created. And then click Attach Policies to apply them to the execution role. Return to the Lambda console and refresh the function's resource summary. You should now see Amazon SES, Amazon Bedrock, and CloudWatch logs listed. For Amazon Bedrock, the managed policy specifies the action allowed Bedrock Invoke Model for all Bedrock models. In production, it is recommended to scope this policy to the specified model ARNs. However, for demo purposes, this broad access provides flexibility. For Amazon SES, the managed policy specifies the resource ARN and action allowed, ensuring the Lambda function can send emails only from the verified domain, which in my case is digitalden.cloud in the EUS2 region, adhering to the principle of least privilege. Next, we'll add the Python code that powers the serverless contact form. The code is available in this video's GitHub repository, linked in the video description below. The implementation is organized into two main Python files. Lambda function py handles the main form processing logic, and the template.py file contains a template used for generating AI-based quotes. Copy the contents of the Lambda function from the repository and paste this code into the Lambda console's code editor. Replacing any existing code. Next, add the template.py file. In the Lambda console, create a new blank file, name it template.py, and paste the contents from the repository into the file. Notice the following import statements at the top of the Lambda function. This line links the two files, allowing the main function to use the template logic defined in template.py. After adding both files, click Deploy to save the changes. With the code deployed, the next step is to configure the required environment variables. These variables store key settings such as email information and AWS service configurations. Environment variables are key value pairs that store configuration settings separately from the application code. This separation follows best practices in software development, improving flexibility, security, and maintainability. Lambda's environment variables make it easy to manage these settings directly from the console. Each environment variable consists of two parts: the key, which is the name of the variable, and the value, which is the actual data to store. The first variable is receiver email. This is the email address where notifications about form submissions will be sent. Next is sender email. This is the email address that will appear as the sender. Since the domain is verified in Amazon SCS, we can use any email address under this domain, like no reply, contact, or even hello. Now we add the sender name, which will display alongside the sender email in the recipient's inbox. It could be a name, your company name, or your website. SCS region specifies the AWS region for Amazon Simple Email Service, which needs to match the region where the SCS domain was verified. The Bedrock region variable specifies the AWS region where Amazon Bedrock is available, ensuring the function can access the Bedrock service in the correct region. If you don't yet have access to Amazon Bedrock, that's okay. We will request access and configure the permissions later. For now, set it to US East 2. Finally, Claude Model ID specifies which Claude AI model the Lambda function will use. We're using the Haiku model because it's well suited for generating concise and impactful quotes, making it ideal for this use case. You can always come back later and use a different Claude model by simply updating this variable in the environment configuration. This flexibility allows you to experiment with different Claude models without modifying the Lambda function code. However, keep in mind that our Lambda function uses the Messages API, which is specifically designed for Anthropic Claude models. As a result, only Claude models are compatible with this implementation. Once all the variables are added, click Save to apply the changes. With the environment variables configured, our Lambda function is now ready for testing. These settings ensure the function can send emails and generate AI-based quotes without hard-coding sensitive information into the script. Now it's time to create a test event that simulates a form submission. This will help us verify form data processing, check AI-based quote generation, test email sending functionality, and confirm error handling and logging. Testing at this stage is crucial for catching any issues early before integrating the Lambda function with API Gateway. Go to the Test tab in the Lambda console and give the test event a name. Next, copy the JSON code for the test event provided in the GitHub repo and paste it into the test event editor. Basically, this JSON simulates the event API Gateway would send to the Lambda function. The body field contains the form data, including a name, email, and message. Be sure to add your actual email address, as this is where you will receive the test email messages. Save the test event. Click Test to run the function. and then expand details. So, when the Lambda function is tested, the simulated form submission triggers the function successfully. The response body confirms the function completed with a 200 HTTP status code and a success result. The Lambda function sends 2 emails as intended. A notification email is sent to the receiver with the form submission details, and a confirmation email is sent to the submitter with a fallback quote. So the Lambda function includes a fallback mechanism in the code to make sure users still receive a response even if the Bedrock integration fails. Let's investigate this issue further. If you look in the log output section of the test event summary, click this link, which will take you directly to the log streams page in the CloudWatch Logs console. Now each log stream shows the logs for a single run of the Lambda function. Select the latest log stream to review the execution details. Here you will see an error event which states error generating quote, an error occurred, access denied exception. When calling the invoke model operation, you don't have access to the model with the specified model ID. Basically, this error confirms that the Lambda function attempted to invoke the Bedrock model but lacked the required permissions to access the specified model ID. So despite the Bedrock error, the Lambda function executed successfully, demonstrating resilience through its fallback mechanism. The logs also reveal key execution metrics like the execution time and memory usage, which confirm that the function's current memory allocation and timeout settings are adequate for this operation. So now that we've identified the issue, the next step is to enable the intended AI functionality by requesting access to the required Bedrock models. If you've never used Amazon Bedrock before, I recommend starting with my lesson here. Now go to the Amazon Bedrock console and make sure you're in the same AWS region specified in your Bedrock region environment variable. On the left-hand navigation pane, click Model Access, and if you already have access to other models, select Modify Model Access. If not, click Enable Specific Models. Request access for all Claude models, including Haiku and Sonnet. And then once done, wait a few moments or click the refresh button to confirm that access has been granted. To verify, you can also go to the provider section, click on Anthropic, and you will see a list of the models granted access. If you click on the Claude 3.5 Haiku model, you will see that this is the same model referenced in your Claude Model ID environment variable. Also note that you can use the provider section to find model IDs for any available Claude models if you wish to update your environment variable to a different model in the future. Now that you have access to the required models, let's rerun the Lambda function test and observe the results. The function will execute successfully again. However, if you check the details in the logs, you will notice a new error message if you're using a model that requires the use of an inference profile. Simply put, this error occurs because the Lambda function is configured to invoke the Bedrock model using on-demand throughput. On-demand throughput refers to the default method of processing inference requests, where requests are processed directly in the region you specify, subject to the service quotas for throughput and token limits. However, some models, like Claude 3.5, do not support on-demand throughput and instead require the use of an inference profile. To address this limitation, Amazon Bedrock provides a feature called Cross-Region Inference, which allows you to distribute model inference requests dynamically across multiple AWS regions. This helps overcome challenges such as service quotas or traffic bursts. So instead of relying solely on a single region to process your requests, Cross-Region Inference routes requests to additional regions as needed based on traffic, demand, and resource availability. For example, the inference profile for the Claude 3.5 Haiku model includes the regions US East 1 and US West 2. If your Bedrock region environment variable is set to US East 1, Cross-Region Inference can route requests to US West 2 when resources in US East 1 are constrained. This happens seamlessly without requiring significant code changes or additional routing logic. By using Cross-Region Inference, your application can handle peak traffic seamlessly, achieve higher throughput by routing requests across multiple regions, and maintain secure and efficient data transfer across the AWS network. Now that we understand how cross-region inference works, let's implement it in our setup to resolve throughput limitation errors. In the Bedrock console, click Cross-Region Inference in the navigation pane. Find the profile for Claude 3.5 Haiku and copy its ID. Go back to your Lambda function and replace the Claude model ID environment variable with the inference profile ID. Save the changes and rerun the test event. The function should now run successfully, generating a quote without any throughput errors. In the log output section, you will notice the function executes successfully without any errors. The logs confirm that the Bedrock model invocation works as expected, and the function processes the request smoothly. You'll also receive 2 emails: a notification email with the form submission details sent to the receiver's address specified in the environment variables, and a confirmation email sent to the form submitter that now contains a dynamically generated quote from the Claude model instead of the fallback quote. This successful invocation demonstrates that the inference profile setup resolves the throughput issues and enables seamless integration with the Bedrock model. With the successful test run, this concludes our demo. We've seen how to configure the Lambda function, handle model access issues, and resolve throughput limitations using inference profiles. The function now integrates seamlessly with Amazon Bedrock, generating quotes dynamically and delivering them via email. You've also learned how to diagnose and resolve errors, ensuring robust and scalable AI integration. This setup is now ready for deployment in a live environment, providing reliable and an engaging user experience. Great work! In the following video, we will set up API Gateway to connect our Lambda function to a publicly accessible endpoint, which will allow users to submit form data and trigger the AI-powered quote generation process in real time.